如果我们从一个非常非常大的尺度来看宇宙的话，宇宙其实是有自身结构的，也就是天文学家们常说的宇宙网状结构。这些结构由恒星、星系、气体、普通物质和暗物质等等构成。有很多人把这种结构类比到人体内的神经网络，但事实上，这些结构要比神经网络复杂得多。这期视频，我邀请到了法国国家科学研究中心专门从事宇宙学研究的 Nabila Aghanim。Nabila 他曾经深度参与过 Planck 项目，目前的研究方向为在宇宙网状结构中寻找那些丢失的物质。今天我们就要和他一块聊聊宇宙网状结构和那些丢失的物质。我是宇宙，欢迎收看我的科学频道。
So my name is Nabila Aghanim. I'm a researcher, astrophysicist. I'm working in France, in Orsay, which is a town south Paris. And I'm working mostly on cosmology, in particular on the cosmic microwave background, but also on large-scale structure of the universe, that is galaxy clusters and the cosmic web.
我记得您说过，您也为 Planck 工作过。
I have been very much and deeply involved in Planck. In fact, I have worked in Planck since my PhD, and for the full part of my career, either working on the preparation of Planck, the exploitation of Planck, and now I am also involved in Euclid satellite for cosmology. So part of my research is also indeed related to space physics, preparing, conceiving, exploiting data from space instruments.
我们要不要先从消失的重子物质说起？是什么时候意识到这个问题的？
So the missing baryon issue is a very old question that has been in fact raised by the fact that there was a discrepancy found between the amount of baryons that the cosmologists predicted from the observations of the cosmic microwave background and the observations at a later time in the recent universe made from the counting or the budget of baryons in galaxies, in galaxy clusters, in gas in Raman alpha, etc. And those two values were discrepant, and numerical simulations have proposed that these missing baryons were mostly hidden in the cosmic web, in the filaments of the cosmic web.
另外一个问题就是什么是宇宙网状结构？
So the cosmic web is the way matter and galaxies are organized in the universe. So when we look at the sky, we see a projection of galaxies. But if we were to look deeper, and in particular, if we were to look 3D, we would see that the galaxies are not randomly distributed over the sky, but they are organized and they are aligned in filaments. Those filaments intersect and form nodes. The filaments in 3D are in fact sheets, they're walls that surround big voids, and all of this is a network of filament, walls, nodes, and voids that we call the cosmic web.
我们可以看到宇宙最初始的样子，也就是宇宙微波背景 CMB。那宇宙微波背景非常均匀一致，宇宙演化到现在是和 CMB 有非常大的区别的。但是到底是什么原因导致了现在的宇宙是网状结构的？
So indeed, the cosmic web is a distribution, or at least it gives us a picture of the distribution of the matter, and we see that it is very homogeneous and it's very isotropic. What makes the structure form is gravity. So the gravitational forces that pull the matter together to form the objects, they don't do it in a spherical manner, but they have very tiny asymmetries, and these asymmetries will end up producing a collapse, which goes first as a pancake, then as a filament, and then as a node. And all of this, if we generalize it, and if we of course run numerical simulations and big computation, ends up into this very non-homogeneous distribution of matter that is called the cosmic web.
您说过这些消失的质量、消失的物质，其实都是藏在 宇宙的这些丝状结构里面的，也就是说要发现这些消失的质量其实并不容易。
So indeed, the missing baryons from numerical simulations is hinted to be in the filamentary structures of the cosmic web. And what simulation tells us as well is that these baryons that are sitting in those filaments of the cosmic web, they should be rather low temperature and very low density, which means that they are not easily detected because they cannot emit X-ray enough so that they're detected, and all the observational signatures that we can have of them are basically missing. So indeed, it's very complicated to detect.
虽然这些网状结构和消失的质量非常难以探测到，但是我们还是有办法去研究它的，对吗？
So it is very difficult to detect individually at one filament level. It is very difficult to pick up a filament and to identify where is the missing baryon. But what we have used in our analysis is a statistical approach, where what we have done is pile up the signal from many filaments, from tens of thousands of filaments that were observed in the galaxy surveys. And by piling up the signal, what we do is not only we increase the signal to noise, but we also reduce all the spurious signal which comes from other parts. And when we highlight the information and the signal coming from the missing baryon in the filaments with respect to the background. And then, by piling up, what we have somehow is an average signal of all the filaments that we're detecting, out of which we can derive physical properties of those missing baryons.
在你们研究这个项目的过程中，有什么有趣的发现吗？
So the first thing was that, of course, simulation said there are hints. Maybe the filaments are the missing baryons are in filament. Maybe you can find them. But before our work, nobody had identified the missing baryons in the cosmic web filaments. So that was the very first part and the very first thing that we have done, which is the discovery of them. And then what we have learned from them is their physical characteristics. So we have learned, for example, that their temperatures are of the order of a million kelvins, that their densities are of the order of densities which are quite low, 100 times lower than the densities in clusters. What we have learned also is how the different filaments are filled with different type of gas. Some cases rather hot gas, some cases warmer gas, and these are the type of things that we learn from them.
Okay. 您刚才提到这些结构的温度可以达到100万摄氏度，但是对于公众来说，当大家一提到太空，就会想到绝对零度，零下273摄氏度。公众和我们对于宇宙的认知或许是相悖的，所以到底是什么因素才可以导致这些结构可以达到这么高的温度的呢？
Yeah, so in the universe, and in particular when objects form, there are those objects, and the universe itself is made of what we call dark matter. So this is a component of the matter that we don't understand and we don't know yet the nature, but which is interacting via gravity. So it pulls the matter together via gravity. So this dark matter coexists with the ordinary matter, the baryonic matter. The baryonic matter is what makes us, what makes the Earth, what makes everything which is surrounding us. This baryonic matter coexists with the dark matter. So when the matter is pulled together, not only dark matter is pulled together, but also baryonic matter is pulled together. And this baryonic matter is compressed and it's heated by the gravity, by the gravitational potential. So the largest the object is forming, the hotter the matter is in, because it is heated by this gravitational potential. So in reality, in the most massive objects that are, for example, galaxy clusters, temperature of the baryons, the temperature of the gas, can reach up to 10 to the 8 Kelvin. Whereas in the outer space, when the gravity is low, indeed the temperature is low.
想一想，这个事情还是挺惊人的，因为引力主导了时间，主导了空间， 它让宇宙形成了这样的网状结构，它让这些结构的温度保持在了一个非常高的状态。
Gravity is indeed the ruler of the evolution of the universe. Gravity is what makes the structures, what it makes the planets, the stars. And then, of course, there are very complicated physical processes that enter into play. So, for example, when the gas is heated, the heat of the gas is escaping. It either escapes via the radiation of the temperature, but it can also escape via the emission of certain lines. So there is a very complex interplay between the gravity, which pulls things together and basically shapes the universe and the distribution of matter, and the very complex physical processes that we know, that normal physics, which make the light. Which is why we always say that light follows matter. That is, the light of galaxy follows the gravity, but in a biased manner. That is, in some regions we can expect to have hot gas, in other cold gas. In some region we can expect to have star-forming galaxies, and in some regions galaxies which do not form stars, etc. But it's a very complex coexistence.
就像您说的，所有的这些普通物质，热气体、冷气体都会随着暗物质而分布。也就是说，通过测量宇宙中的这些普通物质星系，我们就可以探测到暗物质的信息，或者说我们就能了解一些宇宙学的参数。
Because of this very intricate coexistence of dark matter and baryonic matter, wherever we have dark matter, we expect to have baryonic matter. And then the state of evolution of this baryonic matter will depend. In some cases, the state of evolution will permit the generation of stars and hence of galaxies. And in some cases, the conditions will not permit the formation of galaxies. So in some regions, indeed, galaxies will trace the dark matter, but not exactly in a completely fair way because of this these conditions that make galaxies be generated in some cases and not in all cases.
这就是说，我们在做宇宙学研究的时候，要非常注意这些选择效应以及偏差，对吗？
Exactly. Because of these conditions that stipulates that in some areas we have galaxies and in some we do not have, we cannot just use the galaxies as they are for cosmological analysis. We definitely have to take care of the selection effects. We have to make sure that we select similar galaxies in similar conditions so that we do not mix evolution of galaxy effect with cosmological fundamental effects.
Okay, I see.
我知道您同时也在参与 Euclid 的项目，以及之后的几年里 LSST 也会开启巡天观测，对宇宙进行研究。您对之后有什么计划吗？会用 Euclid 或者 LSST 的数据做些什么吗？
Euclid and LSST will be fantastic and great. What we have been able of doing today with the detection of the missing baryons and hidden baryons in the universe, we did it with an old survey which is called SDSS, the Sloan Digital Sky Survey, which was covering only 1/3 of the sky and for which the depth in terms of galaxies was rather limited. With Euclid and LSST, with Euclid in particular, we will have from space a vision of the full extragalactic sky. So we will have the full distribution of galaxies with much deeper, much deeper in terms of distance from us. And with this, we will be able indeed to recover and to reconstruct the full distribution of the galaxies in the universe. And we will have as well the capability of measuring the properties of the galaxies themselves and to refine our selections and to understand how the galaxies and the gas and the dark matter coexist and evolve. And most of all, what we hope to do with Euclid and LSST is to try and answer this very intriguing question of the accelerated expansion of the universe, that is, measuring the properties of the dark energy and hopefully understanding what it is and what it causes this acceleration of expansion.
好啦，这就是这期视频的全部内容啦。如果你喜欢物理，喜欢天文，别忘了加关注。我们下期再见吧，拜拜。